Hi, this is Grzegorz from Nvidia. In this video, I'm going to show you how to get a neural network model from PyTorch framework into production environment. So and my colleagues, we have asked ourselves how much effort it would take to build a conversational AI from PyTorch models. Our starting point was the deep learning examples repository on GitHub, which is maintained by Nvidia. And in this repository, we have various models implemented in frameworks such as MXNet, TensorFlow, and PyTorch. And as you can see over here, we have the ingredients to build our conversational AI system, which is language modeling, speech recognition, and speech synthesis. So I'm going to show you now a demonstration of what we have achieved. So I'm going to play the question I asked to the system, and given the context, it will produce the answer.
Why did the man go into a shop?
And here is the answer from the system.
To purchase sunflowers on the occasion of All Saints' Day.
So yeah, as you can see, this is not a full-fledged application. It is more like a proof of concept, but you can already see what we can achieve with the PyTorch models from the deep learning examples repository. So over here we have a screenshot of our implementation. At the top, there is a record button where we can record the question using microphone. Then this question is translated into text, and given this text and the context, the language modeling model will produce the answer. This answer in the form of text is then provided to the text-to-speech synthesis to first produce mere spectrograms, and from these spectrograms it will give us the audio response. So let's take a step back and see what's the process of producing a conversational AI system. So at the beginning we need a selection of models. So in this case it is automatic speech recognition, natural language processing, and text-to-speech. We also need a framework, so we use a PyTorch over here, and an inferencing system, which is in this case is TRTIS Inference Server, developed at Nvidia. So these are the three ingredients, let's say, that I will describe in more detail in the next section. And well, after we have implemented the models in the PyTorch framework, we assume we have a trained model which was fine-tuned to provide best performance and accuracy. And well, to get from these trained models into TRTIS Inference Server, we have to export the model to one of the intermediate representations that are supported by Triton. So this will require some model preparation. That means some changes in the scripts, such that we can export the models. After we have exported the models, we can then prepare them for deployment. That is, build a directory structure that is read by TRTIS Inference Server, run the server, and run the client that will manage our conversational AI. So let me now talk about the ingredients, that is the neural networks, the PyTorch framework, and TRTIS Inference Server. So our conversational AI system consists of three parts, that is automatic speech recognition, natural language processing, and text-to-speech system. And each of these parts have corresponding, let's say, area in our conversational AI demonstration. So at the beginning we have Jasper model, and which will accept our audio input. Then we have BERT model, which will, given the context, answer to the question stated. And at the end we have Tachotron and WaveGlow that will synthesize audio from the given answer. So these are our four models that we have used in our conversational AI system. Jasper is an end-to-end convolutional neuroacoustic model that uses only 1D convolutions, batch normalization, ReLU, dropout, and residual connections. At input, it takes the audio from the microphone, and it then extracts MEL spectrograms, which are fed into the Jasper model. Jasper produces probability distributions over characters per frame, and these distributions are then processed in the decoder, which, equipped with a language model, will provide a text sequence that is most likely and that best matches the input audio. The output from the Jasper model is fed into the natural language processing model. In this case, it is BERT. BERT stands for bidirectional encoder representations from transformers. And given the question and a passage text, it will predict the answer to the question stated. In the preprocessing step, the model will tokenize the input. That is, it will split the words into segments of integers. Those integers are fed into the BERT model, and the output of the BERT is the probability distribution over the start and end positions within the passage that correspond to the answer to the question. After the post-processing step, we get the answer in the form of a text. Finally, we have the text-to-speech system, which consists of Tacotron 2 and Waveglow models. Tacotron 2 is an autoregressive sequence-to-sequence model. So autoregressive means that the model feeds on its output, and it consumes a variable size input and produces a variable size output. Waveglow, in turn, is a generative flow-based network that takes the MEL spectrograms from the Tacotron model and produces audio waveform at the output. So here we have the sequence of beginning with the text from our BERT model, which is turned into integer representation, fed to Tacotron, Waveglow, and at the end we get the audio waveform. All of the presented models were developed in the PyTorch framework. PyTorch is an open source deep learning platform that has very intuitive API. It has first class Python support, so we can use callable objects or for loops inside our model script, and therefore it gives us great freedom during the development. This is the reason why it's also a very popular research tool. Since it's Python based, it is, however, hard to deploy. And the solution to that problem is the Torch script, which is a statically typed subset of Python, and it gives us better efficiency, better performance during inference, because the Torch script kind of compiles the model to a C++ library and tries to optimize both the model graph and the tensor operations for best performance. Since it's a subset of Python, it doesn't give us as much freedom of development as the PyTorch does. So finally, our third ingredient to the conversational AI system is the TRTIS Inference Server. So Triton supports a number of backends, so this is very practical for our system because specific models are exported to different representations. So we will take advantage of this feature. Also, Triton supports ensembles. This means that we can chain together a number of models and treat them as one model. And in this case, we can also benefit from different features such as scheduling and batching, and also concurrent model execution. Last but not least, Triton is open source, meaning what you can do in case some layer or some functionality is not implemented yet, you can do it yourself by creating custom backends. Here's a diagram of a Triton Inference Server that runs a node with one or multiple GPUs. The Triton Inference Server has several components. So one of them is model repository, which we will populate with our models for conversational AI. And these models will be managed by a model management system inside Triton that will load, for example, the latest version of a specific model, or unload models that are removed from the model repository. In our application for conversational AI, we accept the audio on the client side from the microphone, and this audio is then sent to Triton Inference Server. And because we might have many requests, these requests are then managed by a scheduler that sends those requests to specific backends. And so depending on what representation we chose for a specific model, a corresponding backend will be used to execute that model. So after all the models have run the inference, we can send the response back to the response handling segment of the Triton, and in turn to the client that will produce the output audio. So in this section, I'm going to talk about model preparation, and I'm going to focus on two models, that is Tacotron and Waveglow, where I will show you what changes have been made to the models to export them to Onyx and TensorRT, which is the case for Waveglow, and to Torch script for Tacotron too. So just to review where we are now. So we assume we have trained our model using the deep learning examples repository and the provided model scripts. And now we would like to export the checkpoints to one of the representations that is accepted by the Triton. So the general problem we are facing here is that the frameworks, different frameworks, and the representations, they have different set of instructions or set of functionality that they provide. So it might happen that, for example, we use some layer or in the Python or PyTorch model, but it is not supported by either Onyx or TensorRT. And what we need to do, or in order to be successful in exporting the model, we would like to land in this area, which I called here a happy place, that has all the instructions or functionality common to all the representations. And the approach we have taken here is that whenever we have approach some difficulty with exporting the model to either Torch script or Onyx or TensorRT, we go back to the initial PyTorch implementation. So what one could do is, for example, instead of going back to the PyTorch, we could, for example, modify the let's say Onyx representation such that we can now export it to TensorRT engine, and it will be like a feasible solution. But the drawback of this approach is that whenever we change something in this let's say intermediate representation, we have to take care or maintain this specific representation separately. So we thought that it's better to go to PyTorch implementation and do all the changes over there. In this way, we have only one place where we have to maintain the model. So there are two approaches to exporting a model to either TorchScript or Onyx representation. So this is either tracing or scripting. So in the case of tracing, which is provided by both TorchScript and Onyx, we just run the model on the example input, and report or record all the operations that were executed during this inference. And these recorded operations will always be used during the inference in the exported model. This means that, for example, if we have some if condition and during the export we use only one branch, then in the exported model only this branch will be executed. So to remedy this problem, we can also use scripting, which is only provided by the TorchScript. And in this case, the Python code is analyzed by Torch, and it will correctly capture all the Python constructs such as for loops or if conditions. And depending on the model structure we have, we might just use the Onyx export, which is a go-to approach. But in the cases where we have models that use some control flow, we are better off when using scripting. So in this code snippet, you can see an example export calls. So here we have, for example, a WaveGlow model that is exported to Onyx, and a Tacotron model that is exported to TorchScript. So, as I said, ideally we would like to take any model in our conversational AI and export it to TensorRT, and that would be done using Onyx export. The problem here is that, for example, in the case of Tacotron 2, the lengths of inputs and outputs would be fixed in the exported model. So here we decided to use Torch scripting. And as you can see in the simplified Tacotron architecture, the model uses the MEL spectrogram from the output and feeds it back to the input. And this loop is executed using a regular Python loop. So this would not be correctly captured by Onyx export. So the changes we have made to the model, or what we actually additionally had to write to be able to export the model, is that we had to prepare a wrapper for the inference method in the model. So Tacotron has a different forward and inference method, meaning the forward from training behaves differently than the, let's say, forward from that is used during the inference. And well, what we theoretically could have done over here is use the to use the PyTorch or torch script decorators to let the torch script know that the forward method should be ignored and that our inference method or infer method should be exported to torch script. Unfortunately, well, Triton expects that the exported model will have a forward method implemented. So what we have done is we have taken the model class and wrapped it in additional tacotron forward is infer class that has simply just one method, which is forward, and this internally calls our original infer method. So using this approach, we can export the model to torch script and use forward method in Triton. Additionally, well, during the development of Tacotron 2 model in PyTorch, dynamic attribute creation was used in the model, meaning depending on the size of the input, respective attributes were created with correct sizes for the given input, and those were then used internally in the Tacotron methods to do the processing. For TorchScript, this is no longer possible because, as you can see, it expects us to define all the attributes in the init method. So what we needed to do in this case is to change the attribute tensors to local variables and pass them between calls to the code method, such that they were given both as input tensors and as the output to the code method. This solution works perfectly well, although it clutters our code a bit. So with these modifications, which are also working very well during training, we are able to export the model to TorchScript, and in the snippet on the bottom you can see how we can do it just with a few lines of code. For WaveGlow, we have taken another approach. So here we were able to export the model to Onyx and then to TensorRT, but it required some changes in the or some additional code to be able to do it. So the problem at the moment when we were implementing the export was that 1D convolutions were not supported by Onyx, so we had to change those convolutions into 2D convolutions. And second change, which you can see over here, is that in the WaveGlow model, some of the matrix inverses are initialized on the fly, and this cannot be done during the export. So what we have to do is to run a dummy inference to initialize those inverses and then do the export. So in this code snippet you can see the method to convert 1D convolutions into 2D convolutions. So this has been done for all the convolutions in the model. After we have done these changes, these modifications, we can now export the model to Onyx. So we just provide a modified model, Then we provide the inputs as a tuple. We name those inputs so that we can then use those names, for example, in the Triton configuration. And we also specify which dimensions of the inputs and the outputs are dynamic. So here we would like to have a variable batch size, as well as variable input and output lengths, because the number of MEL spectrograms that are produced by the tachotron varies from inference to inference. And now with the exported WaveGlow model to Onyx, we can load it in another script and build a TensorRT engine. So in this script, we can specify, for example, that the batches will be explicitly provided, so that they can vary from inference to inference. And we can also specify other configuration characteristics such as minimum, optimal, and maximum tensor sizes that will be used during the inference. So this configuration will help the TensorRT to find the best kernels that should be used during inference for best efficiency or best performance. So having those models, we can now deploy them on the Triton Inference Server. In this picture, you can see a diagram that represents the client-server configuration, and we have taken this approach where we do the audio record and all the processing or pre-processing on the client, and the engines from the models or the models themselves, they sit on the server. This approach allows for easy debugging because we have most of the code on the client side and we can inspect it, and it allows us to deploy the model or the conversational AI incrementally. In the production environment, we would like to move the preprocessing to the server side. So one reason for that is that we want to minimize the communication between client and server, and also we would like to take advantage of all the features that are provided by Triton, such as dynamic batching, queuing, and in general better performance. So in order to deploy our conversational AI, we need to provide a special directory structure for the Triton Inference Server, and in this case, each model has a separate subdirectory, as you can see on the right side, and a corresponding configuration file. So in this configuration file, as you will see in a minute, we have different attributes for a specific model. To run the inference server, we have to provide the where the model repository is, and then also let the server know where to load the models from. To start the client, we just run our client container, and here we have an example configuration on the right. So this is for Tachotron 2, and you can see here that the platform is PyTorch libtorch, so this is a backend for Torch script models. We have set the maximum batch size to 8, and for the inputs and outputs, we specify the names and the type of the input and output, and also the dimensions. -1 means that the dimension is variable, and also here we don't specify the batch size for those specific inputs and outputs, because those are provided explicitly for each run. On the left side, we have an example client. So this is actually not taken from our conversational AI system, but more serves the purpose of demonstrating what happens in the client. So we first load the inference context using the URL provided that connects the client to the server, and we provide the inputs to the model. And those inputs are then used to construct the input dictionary. We also have the output dictionary for the outputs, where we specify that the results should have no format. And at the end, we run the inference. With the described steps, we were able to implement our conversational AI system, and you already saw the demo. And what I would like to do is to encourage you to try this demo yourselves. So it's available on the following under the following link, and it has both preparation script that will take you step by step on the process of downloading the checkpoints and preparing them for the export, and subsequently will also export the models, and it has the demo script that you can see over here and that you saw at the beginning of this presentation. At the end, I would like to draw your attention to some of the tools. So one of them is the deployer developed at Nvidia. It contains a boilerplate code for exporting the models to Onyx or TorchScript using either tracing or scripting. It generates the model based on the provided input data, and it also runs correctness tests to see if if it has been correctly exported. It's available on GitHub, and as you can see over here, we have an example line to export a model using TorchScript trace, and it's pretty simple. What you have to provide to the deployer is the data loader and some modification to the model. I would also like to mention two toolkits. So one of them is the NeMo. So NeMo, or Neural Modules, is a Python framework agnostic toolkit for creating AI applications through reusability, abstraction, and composition. And it uses typed inputs and produces typed outputs. The other one is Jarvis. It is an SDK for building and deploying AI applications that fuse vision, speech, and other sensors. It offers a complete workflow to build, train, and deploy GPU-accelerated AI systems that can use visual cues such as gestures and gaze along with speech in context. So to conclude, what we have learned during the process of implementing the conversational AI system is, well, we need to plan ahead when developing a model and continuously check if the export to any of the intermediate representation works. So it may happen that some layer is not supported anymore, but fortunately what is more common is that layer that hasn't previously worked has been implemented in a newer version. So it's good to check the updates or the release notes of the different backends. Um, Triton allows for incremental deployment, so you can start at the very beginning to develop this client-server application, and as you develop the system, you can move some of those or more and more parts of the system to the server side. And what is good is also to engage in many different forums from PyTorch, Triton, and Onyx. The community is very active, so you can expect people to respond to any issues you have. So to sum up, the conversational AI, it provides already great results. Like I said, it's a proof of concept, but it represents the functionality of the whole pipeline. And in future, we would like to move all the preprocessing steps into the server side and use the ensemble to take advantage of many of the features of Triton that it provides. We would also like to extend the demos. At the end, I would like to point you to some of the blog posts available on the Nvidia developer website. I yeah I wish you a good read, and here are some references that you can use to further investigate the conversational AI models and to get yourself familiar with the toolkits that were described in this talk. So thank you very much for your attention.